Hello everyone, this video is going to be on Chapter 5, Chapter on Gases. So some basic concepts your book talks about: pressure equaling force over area. The units of pressure are ATMs, which can also be in torr and millimeters of mercury, and this is how you convert between those three. Your book talks about these formulas, these laws, but the two main ones you want to remember are the ideal gas formula and the combined gas law. The combined gas law just combines Boyle's and Charles' law, so you can just use this one formula. And in other problems, we'll be using the ideal gas formula, and we'll talk about when you use which equation. And the problems we're going to be solving also talks about standard temperature and pressure, also known as STP. So that just means that the conditions are the pressure is 1 atm and the temperature is 273 Kelvin or 0 degrees Celsius. We want our temperature to be in Kelvin for these gas problems, and so converting from degrees Celsius to Kelvin, you just add 273 to your degrees Celsius to get Kelvin. And you need to make sure you convert to Kelvin. That is very important. Convert to Kelvin. And so this is a pretty straightforward practice problem. Converting from torrs to ATM. And so before we said that the conversion factor 1 ATM equals 760 torr equals 760 millimeters of mercury. And so we're just simply going to say 1 ATM is equal to 760 torr, and here our units are going to cancel, and so we're just going to divide 260 by 760. So you should get around 0.34 ATM. And so for our next problem, we're just going to convert from degrees Celsius to Kelvin. And so we're just going to take our 23 degrees Celsius and add 273. To get 296 Kelvin. So the next concept we're going to talk about is the basics of kinetic theory. So pretty much in order to go from solid, liquid to gas, you need to input energy. And this is a very good graph showing us how heat energy increases as you put more energy into it. You're going to go from solid to liquid and liquid to gas because your particles or your molecules are moving around more. And so when we get into this gas phase, we're also going to talk about ideal gas properties. But first we have a practice problem. So in order to change water from a solid to a liquid, there must be what? Input. And we just said it has to be energy input. In order to melt ice to get liquid, you have to put in some heat energy. And in order to go from the liquid to gas, you have to boil it. So we still have to put in energy again in order to change it from a liquid to a gas. And just as promised, we're going to talk about the characteristics of an ideal gas. So when we solve these problems, we're assuming that the gases have certain properties. And so we're assuming that the gas particles do not interact with one another. We're assuming that because they don't collide into one another, the pressure has to come from somewhere. So we're saying the pressure with an ideal gas comes from the collision of the gas particles with the container. And so if you have a smaller container, you're going to have more pressure because there's more of a chance that the gas particles are going to hit the outside of that container because there's less space. If you have a larger container, then you're going to have less pressure. So those two are inversely related. Collisions between gas particles in the container are not elastic, so there's no energy loss. So when you produce pressure from the gas particles hitting the outside of the container, when that gas particle hits that container, we're assuming that there's no energy lost in that collision. And so the two main laws we talked about in the beginning, the ideal gas law and the combined gas law. And so when you're reading your problem, you need to know, well, which formula do I use? Well, the first formula, this one right here, PV equals nRT, you look for moles or grams in the question. So if it gives you moles or grams, or if it asks for moles or grams, you're going to use PV equals nRT. Temperature, as we said before, has to be in Kelvin. R is the gas law constant. It's 0.0821. It's going to always remain the same whether you're here or whether you're in Australia, or no matter where you are, this is the constant. And you can also see it as, you could also see the units instead of seeing it as this. You can also see it as liters times ATM times moles to the -1 times Kelvin to the -1. And the -1 just means it should be in the denominator, but sometimes you'll see it as this, and these two are just the same thing. N stands for moles, should be a lowercase n. N stands for moles. Volume is in liters, and pressure are in ATMs, and this equals 1, this is a typo, at standard temperature and pressure that we had talked about before. But the pressure can change. So the combined gas law, when the problem does not mention moles or grams, it's a good indication that you want to use the gas law and formula. And the units for this are the same as they were in the ideal gas law problem. Pressure's in ATM, volume is in liters, and temperature's in Kelvin. Don't forget to convert temperature from Celsius to Kelvin. And so we're just going to go over this practice problem really quick. A sample of argon gas at STP occupies 56.2 liters. Determine the moles of argon and the mass in the sample. So which formula do we use? Well, it mentions moles. So that's a good indication that we need to use the PV equals nRT. And so because it's asking for moles, I'm going to rearrange the formula to where it's solving for moles. So I'm just going to divide by R and T. So you have PV over RT equals my moles. And we know from our problem that it's at standard temperature and pressure, so pressure equals 1 ATM. We know the temperature equals 273 Kelvin. R equals 0.0821 liters ATM over moles times Kelvin. What am I missing? PV. Oh, volume. They gave us the volume at 56.2 liters. So when we solve our problem, we have 1 ATM times our volume, which is 56.2 liters, divided by R, 0.0821 liters ATM over moles times Kelvin. And our temperature at 273 degrees, so 273 Kelvin. And our liters will cancel, our ATMs will cancel, Kelvin will cancel, leaving us with moles. So then we're going to get 56.2 divided by, this will be 22.41, so that's about 2.5 moles. And then it asks for the mass, so we have to go from moles to grams. So we're going to go from 2.5 moles of argon, and then 1 mole of argon is 40 grams. So that should give us 100.3 grams of argon is our answer. And the 2.5 moles, because it asks for moles. Asks for moles and the mass. So in the next video, we're going to talk about, we're just going to go over some more practice problems.